We have got 10:47 here, so we'll restart. Everybody see the share screen I've got going on of my circuit?
Yes, sir.
Okay. All right, so we'll wrap up today. We're talking about complete path. A complete path in the book, that's on page 26 and 27. A complete path must exist for current to flow, not voltage. Voltage can exist on a circuit, but for current to flow, you must have a complete path. So what I've got here is my energy source. We'll just call it a generator. All right, I have my light bulb in my circuit right here. And then what am I doing here? I'm coming out of my light. Does anybody know what this symbol is here at the bottom? Who said it? Good job. That is ground. Okay, so I must have a complete path from my energy source through the light bulb, out and down to ground. That's called a grounded circuit. All right, so let's talk a little bit right here. If I introduce a switch into this circuit right here, and that's the normal symbology for a switch, and I open my circuit right there in that area, will my light bulb come on?
No.
No, it won't come on because I've opened my switch right there in the circuit, and thus I have not continued the complete path. I've made a break in it. All right, let's go to the other side of the light bulb. Oops, I got to get back on the drawing pen. I need that there anyway. And I introduce a switch on the other side of the light bulb. Will the light bulb come on?
No.
No, it will not, because once again, I have broken my complete path. All right, that's something you're going to need to remember out there in the world. And when we talk complete path, this has got a lot to do with the safety of your work and how electricity works out there in a system, in a utility system. So anytime that I break the path, no matter where it's at in my complete circuit right here, current will not flow. So let's back up just a moment. My first switch right here, and I'll put the open symbol, that's an O. Where now is voltage present? Do I have voltage present here?
Yes.
And here? Prior to the switch?
Yes.
Do I have voltage presence here?
No.
No, I do not have voltage presence through the rest of the entire circuit prior to, or excuse me, after the open switch. All right, I'll introduce my switch here again. Do I have voltage here?
Yes.
Yes, voltage is present. Do I actually have voltage in the lamp?
No.
Easy.
Yeah, you would.
Yeah, you would. Got voltage present in the lamp, but there's no current flow. It's not lighting up because I need current for the light to light up. Once I go after the open switch, do I have voltage here?
No.
No. Okay, good. You guys got that concept down very well. Now we'll talk current flow. And this actually kind of bounces back to the math problems that we had before. My light is a 100 watt light. And my generator is generating at 120 volts. With my complete circuit, how many amps are flowing on my circuit? What's the math? P divided by E. So it's 100, and you're going to have a decimal number right here, divided by 120. Does everybody have that solution?
It's gonna be like 0.8 something.
0.8 something.
0.83.
Right? So there's 0.83 amps flowing on this entire circuit right here. Now you see why we bounced back to math before. Now that we're using a wattage, we're consuming electricity. We completed our circuit. We've applied a voltage. We're actually now able to compute how much current flow amperage we have on the circuit. All right. Okay. So let's talk about a little bit of the construction here of our circuit. And think of this really as in, I want to try to apply it in the actual utility world out here. So hold on one second. Let's do some erasing. Got it. Go back to our pencil. Okay, I'm going to introduce now a transformer right here. And if you remember in the transformer, I mean, we're only going to be using 120, so we're not going to be using the other leg. The center one is the neutral, and the other one of the other legs, how many volts are on it? On a normal 7200, 200 volt transformer. Remember what the nameplate said?
120.
7200, 12470, and it had 120 over 240. Both energized legs combined would equal 240, but we're only going to be using 120. So I've almost got my complete circuit here. I'll show you how this works in the utility world. All right, as I stand right here, do I have a complete path because I'm erasing all this stuff? Is this going anywhere? Oops.
No.
No, it's not. It's just kind of hanging out there in free space. What do I need to connect it to make a complete path?
A ground.
There you go. Okay. And in turn, the neutral from a transformer is grounded. Now, do I have a complete path?
Yeah.
I do. All right. So you'll hear us say this, and we've said it a couple of times before. You're going to have an energized conductor, which is this one. That's our 120 conductor. And then we've also said the silver wire on the secondary, or the wire that's down below. What do we call that?
Can you repeat what you said?
What do we call the wire? We have 3 primary wires and we have another wire. Or on our secondary that's out on the field, we have 2 black wires and a silver wire. What are the wires that transport to ground? What is this wire?
Neutral.
The neutral. There you go. It's the neutral. And in an electrical system, we take the neutral and we ground it. Well, how do we ground it? We'll come down the pole with a pole ground attached to it, or we'll go down to a ground rod that's in the earth. So here's the things that I want you to get out of it. You got an energized conductor, 120 volts. Once it passes through whatever it's feeding, say it's a house, whatever, you're going to have also a neutral conductor to be able to get back to ground. Neutral and ground are two separate things. All right. Ground is the actual earth ground. It's a ground rod or a piece of copper wire. Sometimes you just ground a pole with a piece of copper wire coiled up at the bottom. The neutral right here, and let me make myself a little space. This is very important to remember. This is being recorded too, so you'll be able to go back on it. The neutral is the transport. Conductor to ground. Okay. That is the conductor through this area right here that I'm able to get back to an earth ground. Any questions there? I've got to have a complete path. Getting my voltage out on a energized wire, that's fairly simple. Do remember, I've also got to get it back to ground somehow. That's why we use a neutral conductor to make a conductive connection or a wired connection back to ground down here at the bottom. All right, so wrap it up here. What time are we holding, Robbie? 10:59, we're right on the mark. To wrap up, how many amps did we say was on the hot wire? 0.83. That's on the energized conductor going to the light bulb. How many amps are on the neutral?
Same.
Paul, was that you?
Yeah, same.
Same. There's 0.83 amps on the neutral also. How many volts are on the energized conductor going to the lamp?
120.
120 volts. How many volts are on the neutral wire going back to ground?
120.
It's going to be 0 until you cut the conductor. Okay? If you open the conductor, then you now have 120 volts. Why? Because I took away my path to ground.
All right. Yeah.
Okay? It's 0 when it's grounded. As soon as I open the conductor, as soon as I make a break in the neutral conductor, you've got 120 volts up to this point. All right? A lot of this is going to factor into the future of how you work on conductors, both an energized conductor and the neutral. I'm sure somebody's going to put an explanation out there here for us. When a bird lands on a wire that has 7,200 volts on it, why doesn't it get burned up? Why doesn't the bird die?
Because it's not grounded.
Right. It's not grounded. It doesn't have a complete path, right? There's no path. It's just sitting there. Correct? Why doesn't a duck land on a energized power line?
Because it's got webbed feet.
There you go. Exactly. Paul's on it. All right. I was waiting for some duck hunters because it has web feet. All right, gentlemen. We're going to get into more of this in detail. What I want you to take away today, and we're wrapping up to get ready to go to the field. No quiz today. No test today. I don't like to give them on Mondays. So let's give a quick wrap up here of what we've gone through and what you need to keep in those data banks and in your notes. Know what alternating current is. Know what direct current is. Unidirectional and bidirectional. Not much in the atom area. We're okay with that. Know what electric flow is and what theory is used. The most common theory, that would be the bump theory. Know what a conductor is, its properties. Know what an insulator is, its properties. Know what a semiconductor is and its properties. Those are in the book. Know how to define the amp and what current flow is. Know the speed of current, the speed of voltage, and the speed of current. That's in the book. And then know what a complete path is. How am I able to power whatever I need to power through a complete path and the properties of it? If I break anywhere in my complete path, the light bulb will not light up. Does the entire circuit carry amperage? Yes. Does the entire circuit carry voltage? Not on the neutral until you break the neutral. And there will be voltage present here. Okay. As far as outside of the teaching today, obviously I had to shut down, so I'm gonna have to restart. There's gonna be 2 videos. Any other questions that we've got going on before we break it? Sounds like Paul's the only one that's awake.
I'm out.
Once you say let's leave, they all kind of scatter, so I know they're kind of listening.
Yeah.
All right, gentlemen, we will meet you on the yard today, 12:30 in the afternoon, and be safe getting there.
See ya.
All right.